Hello everyone, I am Dr. NAVNEET KAUR, Associate Professor in Department of Electronics and Communication Engineering, SIRT College, Bhopal. Today I am taking lecture on subject Signals and Systems. The topic of this lecture is Operation on Signals. Now in this lecture, I'll be discussing various operations on continuous time or discrete time signals. Now first, we'll discuss time shifting of the signals. Now time shifting, which is also called translation, it maps the input signal xt to any output signal yt as given by yt is equal to xt minus b, where b is a real number. Now if b is greater than 0, then y is shifted to the right by magnitude b relative to x. It is also known as time delay of the signal x. Whereas when b is less than 0, y is shifted to the left by magnitude b relative to x. In this case, the signal is known as time advanced version of signal xt. Now, we will understand time shifting of the signal with the help of the example given here. Now, suppose I have any continuous time signal xt, which is defined between -1 to 1, and the amplitude is 3 at t is equal to 0. Now, if I want to shift this particular signal by 1 units to the right, that means I want to delay this particular signal by 1 unit, then it will be termed as xt minus 1. In that case, this signal will be shifted by 1 unit towards the right axis, right along the time axis. Now, in this case, instead of the signal which was defined between -1 and 1, now it will be shifted towards right. So it will be defined between t is equal to 0 and will end at t is equal to 2. Similarly, if I want to draw the advanced version of this particular signal xt, that means if I want to draw xt plus 1, then in that case, this particular signal xt will be shifted towards left by 1 unit. Now, in this case, now the signal will be now defined between t is equal to -2 to t is equal to 0. There will be no change in the amplitude of the signal. Now, next operation is the time reversal of the signal. Now, if I want to obtain the time reversed version of any signal, then I will take the mirror image of that particular signal. That means yt, which will be the time reverse signal, will be given by x of minus t. Whatever the value of the signal xt is at t is equal to 1, now it will be at t is equal to -1, and vice versa. That means whatever the value of the signal is at t is equal to -1, now it will be defined at t is equal to 1. Similarly, it will be true for t is equal to 2, 3, 4, and so on. Now here I can see the signal xt, which is a continuous time signal, and it is having a magnitude as shown in this figure. Now, if I want to find out the time reversal signal of this particular signal xt, then it will be represented as x of minus t. Now, whatever the values of the signal was at t is equal to -1, -2, and -3, now it will be now at t is equal to 1, 2, and 3 respectively. Similarly, whatever the values of the signal was at the right hand side of the t, now it will be defined at the left hand side of the t. That means t is equal to 1 value will now be shown at t is equal to -1. Similarly, t is equal to 2 value will be at t is equal to -2, and so on. Now, next operation is the time scaling of the signals. The time scale signal of any particular signal xt is represented as yt is equal to xat, where a is a positive real number. Now, if value of a is greater than 1, then in that case, the resulting signal yt will be compressed along the horizontal axis by a factor of a relative to x. Whereas if a is less than 1, then in that case the resulting signal will be expanded along the horizontal axis by a factor of 1 upon a relative to a. Now, we will understand this time scaling with the help of an example. Now, this is a signal xt, which is defined along the x-axis, which is defined by time t, and it is defined between t is equal to -1 to t is equal to 1. Now, if I want to draw x2t, now in this case, here value of a is equal to 2, which is greater than 1. So in that case, the signal will be compressed by a factor of 2. That means whatever the value was at t is equal to -1, now the same value will be at t is equal to -1 upon 2. And whatever the value was at t is equal to 1, now it will be at t is equal to 1 upon t. And at t is equal to 0, the value will remain same. So here we can see the resulting signal is starting from t is equal to -1 by 2 and it ends at t is equal to half, whereas at the value of t is equal to 0 remains same. Now, if I want to find out another signal xt by 2, in this case a is having value 1 upon 2, which is less than 1. So here the signal will be expanded by a factor of 2. That means now whatever the value was at t is equal to -1, now the value will be at t is equal to -2. Similarly, at t is equal to 2 will be the new value which was at t is equal to 1. And the value at t is equal to 0 will remain same. So now the signal will start from -2 and will end at t is equal to 2. And the value, the resulting signal will be expanded by a factor of 2. Now, here we can see one more example. Here I have any signal yt, which is defined from 0 to 3 and the amplitude of the signal is 2. Now, if I want to find out y3t, that means here the value of a is equal to 3, which is greater than 1. So in that case, the signal will be compressed by factor 3. So the value at t is equal to 3 is now at t is equal to 3 upon 3, which is 1. So here the signal will be compressed by a factor of 3. Now, if I want to find out another signal, which is yt upon 3, here a is equal to 1 upon 3, which is less than 1. So here the signal will be expanded by a factor of 3. So now the signal which was having the value at t is equal to 3 will now have t is equal to 3 into 3, which is 9. So here now signal will be defined between 0 and 9 instead of 0 to 3. Now, next is the amplitude scaling of the signal. As the name represents, amplitude scaling means that here the amplitude of the signal will be scaled by a factor which is defined by a. So here yt will be given as axt, where a is a real number. Now here the signal yt will be expanded and compressed in amplitude, not on the time axis. Now suppose here the signal xt is represented by this sinusoid. Now if I want to find out 2xt, now here we can see this sinusoid is having maximum value +1 and minimum value -1. Now 2xt will be amplitude scaled by a factor of 2. That means here the maximum value will be t is equal to 2 and minimum value will be t is equal to, maximum value will be at 2 and minimum value will be at -2. Similarly, half xt means the amplitude is scaled by a factor half. Now the maximum value will be half and the minimum value will be -half. Now -2xt means here the signal is now reversed by -2. That means now the value which was at -1, now it will be having value 2. Similarly, which was at 1, now it will be having value -2. So in this case, the amplitude scaling of the signal is obtained. Now, after understanding the basic operations of the signals, now we will see some elementary signals which are important in signal and system analysis. Now, first elementary signal which is commonly used is the sinusoidal and exponential signal. Now, sinusoidal signal, as we already know, it is represented by A sine 2 pi f naught t, where A is the maximum amplitude of the sinusoid and f naught is the frequency of the signal in hertz. Now, f naught can also be represented as 1 upon t naught, where t naught is the time period of this sinusoid. Now, here the radiant frequency omega naught is given by 2 pi f naught, or it is also written as 2 pi upon t naught, and we have already discussed t naught is the time period of the sinusoidal wave. Now, after sinusoidal signal, we have real exponential signal. Now, real exponential signal is A e raised to power at. Now, A is the amplitude and e raised to power at is the exponential form. Now, we can have complex exponential also, which is written as A e raised to power j omega naught t. Now, this is represented in the form of a phasor. The phasor which is having maximum amplitude A and omega naught is the frequency. Now, here e to the power j omega naught 2, as given by Euler's rule, can also be written as cos omega naught t plus j sine omega naught t. Now, here omega naught is the radiant frequency and A is the amplitude of this exponential signal. Now, next signal is the unit impulse signal. Now, unit impulse signal is actually obtained from the derivative of the unit step function. Now, here we can see the unit step function, which is having maximum amplitude 1 upon A, and the width of this unit step signal is minus A upon 2 to A upon 2. That means A. The width is A. Now, here, when A approaches 0, then this amplitude of the signal approaches infinity and the width of the signal approaches 0. Now, here we will obtain a unit impulse signal, which is obtained as the derivative of the unit step function. Now, in this case, we can define the strength of the weight of the signal. Here, this is the unit impulse signal, which is represented as the arrow, and the strength of this signal is 1. The strength is actually the area under an impulse. Now, it is represented graphically by a vertical arrow. An impulse with a strength of 1 is called a unit impulse. Similarly, here we have 5 delta t minus 1. That means this delta function or unit impulse function is shifted towards right by 1 unit, and it is having a strength of 5. So the amplitude shown here is 5. Now, there are some important properties of the impulse function. First is the sampling property. Now, according to the sampling property, if I take integral of gt with shifted delta function, then it will be given as the same function gt, but now it is defined at the point where this delta function is shifted. Now, the scaling property is that if delta A t minus t naught is given upon as 1 upon A delta t minus t naught. Similarly, the replication property is that if I take convolution of gt, any signal with delta t, which is unit impulse signal, then I'll get the signal itself. Now, this is all for today's lecture. Thank you and have a nice day.